So we had inclined planes, and we'll talk about that assignment, and then you've got a lab dealing kind of with inclined planes and vectors and how it all kind of fits together. So here's the story when you have any inclined plane problem. No matter what are the three forces you always have?
Force normal, gravity, force.
So your force normal, remember, your force normal does not act straight up, okay? Your force normal acts at a right angle to that surface. So if this is your inclined plane, and you're like this, the normal force is going to be like this, okay? The only time the normal force acts straight up is if you're on a flat surface. Now, your gravitational force does always act straight down, okay? Technically, that's towards the center of the Earth, if you really want to get picky, okay? Which gets weird, because if you're on the South Pole, then you drop something that actually like falls up, because it's falling towards the center of the Earth. Now, and then you have your force parallel. So those three are all set in a specific direction. You cannot change the direction of the force to parallel, okay? You can't. It isn't like, oh, I'm going to get off the mountain in Colorado, and then all of a sudden, you know, get up the ski lift on top of the mountain, and gravity starts pushing you up the hill, okay? It's not going to happen. It's always going to act down the hill. Home run, always going to act down the hill. Normal, always going to act perpendicular to it. Gravity, always going to act straight down. Those directions are invariant. Where you run into trouble is which direction is applied force going to act, which direction is friction going to act. But friction itself even has its own set of rules. The gravity, or the frictional mafia, always acts in the opposite direction of motion, okay? So if you're pushing something up the hill, friction acts down the hill. If it's going down the hill, friction is going to act up the hill, okay? So that one is just set in stone. It's always in the opposite direction of motion, okay? You just have to figure out which way it's moving. Your applied force can also go up or down, okay? So if Dylan is pushing the mower up the hill, okay, so here's the mower, and he's pushing it, he's obviously going to go up the hill. Now, but by the same token, if the mower is going down the hill and he doesn't want it to accelerate out of control, it's going to go down the hill, but he's actually going to be pulling up to keep it from going down the hill. So, depending upon the situation, your force applied, you just have to look at it in the context of the problem. So, because if number 5 starts wrong, everything is going to go wrong. So your answer to number 5 should be around 4 newtons, okay?
Would be negative?
It's up to you. It's however you want to define your system. If you want down to be negative, cool. That's going to be a negative value. If you want downhill to be a positive value, it's going to be a positive value, okay? I don't care. There's no right or wrong answer to that question. But how you define the system is going to determine everything else that you do on all the way through number 8. So once you establish that system on number 4, you have to use that same system all the way through number 8, because it's all building off the same problem, okay? There's no right or wrong answer, just pick one, okay? So, hopefully what you should see on that acceleration on number 6, okay, should be around 3 meters per second squared. But then, when you get down there to number 8, now that there's friction involved, your acceleration should be a lot less. So, because if you think about it, that should make sense. It's like, okay, yeah, right, okay. I got the same force parallel, friction's acting up the hill, I'm going to have less force available to actually make it accelerate, and my acceleration should be a lot smaller. So your acceleration on number 8 should be less than 1.
Number 8? The first net?
Your acceleration should be less than 1.
On 6.
Number 8.
On number 8. Okay. Now, where it gets a little sketchy is when you get into something like, for example, on number 10. So at number 10 and 11, you have all of these things that are in play. So what I would recommend, not mandatory, is that you set up a chart and you go, okay, on an inclined plane, I could potentially have force applied, I could have force opposing, I could have force parallel, and then I could have my net force. Because if you don't know what the forces are and which direction that they're acting and what the sum should equal, you can't work the problem. You can get the numbers, but if you don't know which direction they're acting, it doesn't make any sense. So, on number 10, what are the two most important words on number 10? Constant velocity. So you want your net force to equal 0. Okay? Because that's the only way you can have constant velocity. So visualize this. Here's this block, right? And you want to move this block up the inclined plane, so you know that your force applied has to act up the inclined plane. Okay, that's it, because that's the direction you're going to push it. Cool, you got that. You know your force parallel is going to be acting down the inclined plane, and there's your FG, and there's your force normal. Okay, so the wild card is, what do you do with the frictional force? So since you're pushing it up the hill, which direction does your force friction going to act? Down the hill. So this is a situation where I don't care how you define the system. If you want to stick with these values being negative, fine. You're going to have a negative force friction, you're going to have a negative force parallel, and then you're going to have a positive force applied. Cool. If that's what you want, great. Knock yourself out. If you want to make the positive going down and negative going up the hill, great. Knock yourself out. So when you get to number 11, the only thing that's different on number 11 is this. You want it to slide down the hill. Okay? You want it to slide down the hill. So if you want it to slide down the hill, which direction is friction going to act? Up. So on number 11, you have the exact same frictional force. The only difference is that now that's going up the hill. So on number 10, your force applied balances out the two forces that are going down the hill. On number 11, your force friction and your force applied balance out the force parallel. So if all goes well, on number 11, that answer should be between like 6 and 8 newtons. And your answer to number 10 should be something around your first teenage birthday, when you thought you were really cool. Oh, I'm a teenager. Wow. Okay. All right. Are we good?
I need help with 11.
With what?
11, I don't understand 11.
Yeah, on 11, you're using the same everything up here, you're just trying to calculate going down.
The only thing that
Okay,
changes.
so then the force friction.
Yeah.
Okay.
Wait, Mr. Burke, patience. Like, okay, so when I drew this, I know it doesn't make sense because I made my force applied positive in the same direction as a negative number, but why would it still go up? Like, why would my force applied still go up?
Because of the fact that when you look at your force parallel,
Yeah,
okay, your force parallel is bigger than your force friction.
yes. Yeah,
So,
like, I know it doesn't make
because
sense, but,
so imagine there's this track, right? Okay. If I want to push it up the hill, obviously I push it up the hill.
Yeah.
Now, if I want to keep it from sliding down the hill, I still have to apply an upward force to keep it from falling.
so
You brought my grades, but
this is the, like,
Force
scenario
gravity
where
is the
force
same for
friction
softball,
and force
so
applied are in the same?
2.35.
Direction.
newtons.
What?
Yeah.
Force gravity is the same.
Makes
as
sense.
2.3.
Yeah.
Got it.
Cause I mean, like, I got, like, the number, like, I understood the math.
Yeah, but yeah, because you're applying an upward force
Still,
to keep it from sliding down.
okay, yeah.
So what you
Yeah,
got
cause
right
we were
here?
gonna have
yeah.
upward force would go even,
Yeah,
yeah,
Oh, wow.
okay, that makes,
makes sense?
yeah, thank you.
Okay.
Where did you get? Yeah, you're.
All right.
Okay.
Are we good? Going once, going twice, sold. Get that handed in.
Bert, what'd you say 11 would be close to?
Between 6 and 8.
I don't know what you just did.
What?
Oh, wait.
But I'm already coming back.
We'll just deal with it, because we gotta get started on labs. Okay,
That's it. Wait.
so, we need to do a little bit of trig to get ready for one of the labs, which is on inclined planes. So here's what you're gonna do. So I want you to think about this. So if I take this cart and I put it on here, okay? And I give the cart any kind of slope at all, it accelerates, okay? Because it's basically a frictionless surface. But if I take this block and I put it on there and I lift it up, it doesn't move. But if I lift it high enough, at some point, what's gonna happen?
It'll start to fall.
It's gonna begin to move. So why does the cart roll very easily at any kind of, put any kind of slant on it, it rolls? But I put this block on here, I get it to that same angle, and nothing happens.
Friction.
So this is where the two mafias are in battle against each other. So the gravity mafia is trying to get the block to slide down the ramp. The frictional mafia is trying to hold it in place, okay? So right now, who's winning? Frictional mafia. So this is also a classic example of just because I have forces acting on a system doesn't mean that it's going to accelerate, okay? So I do have a force parallel acting down. I've got a force friction acting up. I've got a normal force. I got gravity. I got all these forces acting on the system. It's a very complex system, but it's just not accelerating. Now, at some point when I lift this up, it's just going to begin to move. Right there. So what do you call that type of friction where it's moving from rest?
Static.
Static. So you have kinetic, which is in motion, and you have static, which is from rest. Okay? So here's the assumption that we're going to make. Is that when you lift it up and you find that point where it just begins to move, it just breaks loose, what we're going to assume is that the force parallel acting down is equal to the force friction, which is holding it in place. It's just like you did when you pulled the blocks, okay? Remember you had the blocks, and you increased the force until it just began to move, and that force that you applied was the frictional force. Same thing is going to happen here, okay? And you still got your force normal. So here's the whole key to this. We're going to set the force friction equal to the force parallel. Now, you know that mu, coefficient of friction, equals force friction over force normal. Okay? Standard definition of mu, no matter what. This is a standard definition. Now, we said force friction is going to equal force parallel. Okay? That point where it just begins to move. And this only works for static friction. This only works for static friction. So I go, okay, well that's the same as my force parallel over my force normal. Well, force parallel is Fg sine theta, and force normal is Fg cosine theta. Fg's cancel out. So for those of you that have studied trig identities, this is your one chance. This is your one chance outside of a math classroom to use trig identities. What's sine over cosine?
Tangent.
Tangent. This is your one shot to ever use trig identities outside of a math class. Glad you took it. So mu equals,
You're gonna win, right?
tangent theta. Now, it only works, listen to me, this only works for for static friction, when the block is beginning to move. If you're pulling it, it doesn't work. This is only when it's coming from rest. So, you've got, in this case, let's say that was 20 degrees. All you have to do is take the tangent of 20, boom, there you go, there's your coefficient of static friction. Okay? Now, obviously, if you have a low friction surface, what's going to happen to that angle? It's going to be bigger or smaller when it begins to move.
Smaller.
Much smaller, okay? So the less friction there is, the smaller that angle is going to be when you overcome it, because there isn't just as much friction to overcome. Okay, so let me hand out the first lab. Oh, there's two.
The end.
I forgot to turn this in yesterday.
Ed,
I figured out why I didn't get one back.
That would explain it.
I had it and I was gonna turn it in, and I think I started packing up and just threw it in my folder.
Okay. Morning. Okay, so the first lab is going to be on inclined planes. So there's going to be two distinct parts to it. So notice in big bold letters I said, show all calculations, okay? Numbers that magically appear bad. So the first thing that you're going to do is that you're going to take a block of wood, put it on a plank, just like this. You're going to lift it up like this until it just begins to slide. Measure the angle, take the tangent of it, boom, there you go, coefficient of static friction. Perfect, okay? Not a problem. Second one's going to be more complicated. So on the second one, you want to set it at an exact 30-degree angle, okay? Call me over, I've got my phone, I got an app, we'll measure it so it's exactly 30 degrees. So this is going to be important. You're going to know what the angle is, okay? You're going to know it's 30 degrees. Now, how are you going to get the weight of the block? Do not make this difficult.
Newton scale.
Take a Newton scale, hang it up, boom, there you go. Okay, there's the weight of the block. If you know the weight of the block, and you know it's a 30-degree angle, what can you find?
force parallel.
And?
Force normal.
Force parallel and force normal. Okay, so then you can find those numbers. There's no gravitational force. So then what you're going to do, take a Newton scale, oddly enough, and that's going to be set at 30 degrees. You're actually going to have this held up with a ring stand. I'm just going to do it myself. So you're going to have this thing set the way around at a 30-degree angle, like that. And then you're going to pull it up at a constant velocity, which is like 2.82 newtons, whatever that number is. So what is this measuring? Force applied, force parallel, force normal, gravitational force, or force friction. You have 5 choices.
Net force.
What's your net force going to equal?
0.
Why?
Because it's at constant velocity.
Because it's a constant velocity.
Force
So if
applied.
this was measuring net force, what would it read?
0.
So
Can't be that.
Force applied.
Force applied. Because that's how much force you're applying to the block to make it move. So here's what you've got. So this is just, instead of like calculating it, you're going to measure it. So you've got this thing set at an exact 30-degree angles, right? So you can determine the force parallel, okay? Get your FG, force normal, boom, there you go. And you're going to measure the force applied, okay? You're going to measure that. So let's just say, to make the math easy, let's say that you calculate your force parallel using FG sine theta. And let's say that that force parallel was -3 newtons, and you want it downhill to be defined as negative. And that's one of the things that on this, what you need to decide. On the sliding friction in your system, downhill is defined as blank, and uphill is defined as blank. There's no right or wrong answers to that question. You decide. But again, once you take that to the dance, you got to stay with it at the dance. Okay? So if you want downhill to be negative, fine, great. It's negative. If you want downhill to be positive, great, downhill is positive. I don't care. So, let's say you want downhill to be negative, right? And you measure your force applied, and let's say that that's 5 newtons, right? So, you're at a constant velocity. This is your applied force, right? That's how much the Gravity Mafia is charging you. So you have $5. The Gravity Mafia is charging you $3 to move the block up the hill, okay? How much is the Frictional Mafia charging you?
Must be 2,
2. Why?
because net force is 0.
Because the net force is 0. So you're trying to pull this up the hill. Big Tony, right, and Joey are going, we need to talk to you, okay? You're a good boy. So you got the force parallel going down at -3. Then your force friction is going to be the difference between those two to pay off the Frictional Mafia. And that's going to be -2 newtons. So here's the deal. You never directly measure the force friction. Do not ask me, go, hey, Burkham, where are the force friction probes? Don't have them. But what we can do is that we can measure how much force it takes to move something. Now, if you're on a flat surface, and it took 5 newtons of force to pull it, what would your frictional force be?
-5.
-5, because those two would add up to equal to 0. But you're on an inclined plane. So now, if you're on a flat surface, you only have to worry about paying off the Frictional Mafia. But if you're on an inclined plane, who do you have to pay off?
Gravity.
The Gravity Mafia and the
Friction.
Frictional Mafia. Okay? There's your Mafia lesson for
I
today.
like that a lot.
Okay.
The Gravity Mafia.
Yeah, it's all about the Mafia. Okay, so you got everything's going to add up equal to 0. So what you're going to do, you're going to have your FG. Boom, hang it up, there you go. You're going to calculate the mass from that number. Do not ask, it's like, Burkham, how do we get the mass from the weight? I will just flip out. Force applied, that's what you're going to measure, okay? So from that, you're going to determine your force parallel, you're going to determine your normal force, you're going to determine your force friction, and you're going to calculate mu. Now, notice in big bold letters up here at the top of the lab, what do I tell you to do?
Show all calculations.
Show all calculations. Let me show you what is not showing a calculation. Mu equaling force friction over force normal. That is not a calculation. You have written down a formula. That doesn't tell me what numbers they use. Is the formula important? Absolutely. But that isn't showing work, okay? We're beyond the point of me tolerating random numbers written down on a piece of paper, okay? Show me the work. Now, you can do this on the back side, you can do it on another sheet of paper, I don't care. But
There's no
you
back
need
side.
to determine,
Oh my, that's peak.
He said we have 2 labs, Gavin.
so this one is drawn to scale at a 30-degree angle. You are going to show all the forces acting on the scale or on the graph drawn to scale. You want to let 1 centimeter equal Newton. Do you want to let 2 centimeters equal Newton? I don't care, okay? But pick a scale. Okay, so that's lab number 1. Second lab. So we're going to start with something simple. So I'm going to take a Newton scale, and I'm going to re-zero it because I'm going to be hanging something up. And I'm going to hang it from here. Come on. Go. And this is just a light piece of string.
Kevin, it's the same table. Probably.
And I'm going to take a 1 kilogram mass, and I'm going to hang it from the string. What should the reading on the scale be?
0.
9.8.
Oh, 9.8. Oh, shoot. I was just looking at it.
So I hook it up.
Is it gonna say 9.8? Oh my
It's
god.
9.81 actually.
9.81. Okay?
Boy.
Why does it read 9.8?
When it's
Because,
gravity,
yeah.
it's not
Gravity
acceleration.
acceleration, people think.
Okay? Is the system accelerating?
Nope.
Mm-mm.
All the forces add up to?
Zero.
Zero. Okay? So right now, I've got, by the way, Caitlin, spin that camera
I
around.
have a question. This is a good question.
Okay?
Is their force normal acting on that right now?
No. And I'll tell you why. This, you can call this tension.
Force tension. Okay.
Normal is provided by like a solid surface.
Okay.
The string is, because the normal force would be here from like a table.
Okay.
Okay? So we call this force tension.
So this force tension is basically your force normal then.
Yeah. Divided by a string. Now, it's a simple idea. You add them together, what do you get?
Zero.
Zero. Cool. Okay? Now, let's change it up a little bit. So, imagine that you are holding a bucket. Okay? So here's your arm, and you're holding a bucket, right? Got water. And you're just standing here. What's the value of the upward force relative to the downward force? Same, bigger,
Same.
same. Now, imagine that you're gonna take that same bucket, it's about half full of water, it's got some heft to it. But now, you're gonna hold it out at an angle like this, okay? What's gonna happen to the force that you have to apply?
More.
More, yeah.
More, right? It's harder to hold that up like this, right? Is it harder to hold it up because gravity is pulling down with more force?
No.
No.
No, the same gravitational force is acting down, okay? Now, vertically, is it accelerating?
No.
No.
So therefore, I know this vertical component here is still balancing out that value, right?
Mm-hmm.
But what's happening is that now you have a horizontal component to that force that you didn't have before. So when it's straight down, everything's acting in this direction. You hold it out, it's heavier. Now, keeping that thought in mind, we're going to change up this system, okay? Change up the system. So, I'm going to get another, and here it is. I got another Newton scale. And I'll put that there. Slide it.
Oh, I see where this is going.
Oh, where's it going?
We're gonna get 4.9.
So I'm going to take the same 1 Newton mass, or 1 kilogram mass, and I'm going to hang that up between the two of them.
What did I say, Dylan? What did I say? Oh, what the heck? The other one says 5.
Well, that's because I don't have it quite centered.
Oh. But it should say what I said.
Yeah.
What did I say?
Okay, one's a little bit more, one's a little bit less. But here's the point of the story. Why, allowing for what you're observing, because right now, what's the acceleration of the system?
None.
It's not accelerating. Do you still have the same amount of downward force?
Yes.
Yes. So therefore, my vertical components upward still have to balance out the 9.8.
Mm-hmm.
True?
True.
So vertically, the sum of the forces in the y direction, so that's a technical way to write all the forces in the y direction, have to add up to equal to 0. So that means I'm going to have negative 9.8 newtons. Now, Gavin was right. If, and that's a huge if each one of those was carrying the same amount of force, okay, equal amounts of force, then each one would be carrying half, and we would have 4.9 plus 4.9. But here's the point of the story. Even if it's not an equal distribution, those values still have to balance out that negative 9.8. It might be 6 and 3.8. It might be 4 and 5.8, something like that, okay? But no matter what, these components have to add up and balance up to 0. Now we're gonna change it. Okay, now we're gonna change it. So now, I'm gonna take the scales and I'm gonna slide them apart. Okay, so I'm gonna make like a Y. Okay, make a Y. What's gonna happen to the reading on the scales? 3 things could happen. Reading on the scales could increase, they could decrease, or they could just stay the same, each one being about 4.9.
Ooh, it'll increase.
Decrease.
Are they still equally apart?
Yes,
It'll just stay the same?
both at 4.9.
I think increase,
Yeah.
based on what you said about this bucket.
Mm-hmm.
Okay,
Maybe I'm just a goat.
I think it decreases because of the
Oh.
employing part at the
Oh,
top.
Dylan's different.
you're saying it's gonna decrease, so each one is gonna, might drop to like 4,
Yeah.
okay?
Wow.
Well, let's see what happens. So,
No bueno.
no one.
Oh my gosh, that reads 6 and that reads 5. Oh, they both read 6.
I'm reading 3.
So that's
Three,
like
you
6
reading?
point,
The dictionary?
quit moving. This is like 6.08, and that's 5.99.
What did I say?
So,
We're not.
is gravity stronger?
No.
Sorry.
Gravity's not stronger. What's the acceleration of the system?
0.
None.
So everything still has to add up to
0.
0.
None.
Does this thing still weigh negative 9.8 newtons?
Yes.
Yeah.
So vertically, what we're gonna do is we're gonna break this up like this,
Oh, okay.
okay?
Right triangle.
Right triangles.
Oh, we know the force. Wait, no, we don't. Wait.
Okay? Now, here's what's gotta happen.
Oh,
What?
I figured it out.
What?
So basically, those are the hypotenuses. And when you move it on the x, it makes the hypotenuse bigger.
But are you changing the vertical side of it?
No.
Why?
Because it's still the same height. We still got that same vertical force, but we add a horizontal force.
Excellent. So the reason that the reading on the scale went up is exactly what Gavin said. Because of the fact that now that's the hypotenuse, which is why when you hold your arm out like this, it feels heavier, okay? Because now you have a horizontal component to that force as well. So, mathematically, the sum of the forces in the y direction still have to add up to what?
9.8.
Nope,
0.
0.
Oh, wait, okay. Still,
Okay? So you're gonna have the weight of what's hanging down, right? Which in this case would be negative 9.8, plus Fy1 plus Fy2, okay? So these two values here have to add up to
28.
balance out the negative 9.8, so those two forces there have to add up to a positive 9.8, okay, because that's the only forces that you have, right? So, what you're gonna do in the lab is you're gonna set up a diagram, you're gonna set up a lab like this, you're gonna do this. You're gonna measure the hypotenuse, that's gonna be the reading on the scale. But what else can you measure?
The FX one.
How?
Pythagorean
No
theorem.
FY1,
Nope.
so then,
What'd you say?
wouldn't it be Pythagorean?
No.
So you know FY1 and you know the hypotenuse.
Hold on, you don't know what Fy1 is.
Oh, okay.
But could you measure an angle?
Oh,
Yes.
Yeah.
Oh my.
Ooh, you can measure an angle,
That's how we find it.
and you know the hypotenuse.
Yep.
Trig functions.
Oh, trig functions to the rescue. So if you measured this angle, how could you find Fy2 knowing the hypotenuse?
Sine.
Sine.
Yeah, So in this
Sine.
case, I would take 6.08 newtons times the sine of, I don't know,
32 degrees.
whatever that angle is, 64 degrees, whatever that
Can you
is.
just double put on?
Okay? Over here, how can I get my fx?
Cosine.
Cosine. So now, that's if I measure this angle. Sometimes you're given this angle. Okay, so you have to watch what angles that you're given or what you're measuring. Personally, I always like to work off of this angle out here because it's easier for me to see those x and y components. So, using trig functions, you're going to find the two vertical components. In theory, they should add up to balance out the weight of the object. Okay? What about your horizontal components? How many horizontal components do you have? What do they have to add up to?
0.
So it's the only way two horizontal components can add up to 0.
Equal but opposite.
Yeah, so in theory,
Oh, one of them's gonna be negative.
ah,
Positive. Which is either like left is.
so the sum of your x components should add up to be 0. So fx1 plus fx2 should add up to,
0.
None.
and the only way that can happen is if they're equal and,
Opposite.
because it's kind of like the limb, okay? In the limb, when you're trying to land on the moon, you didn't have any horizontal forces, okay? There was no horizontal gravity or anything. Same thing is happening here. We're not pushing it horizontally. There's nothing. So your horizontal forces are the easy ones because those should just add up to equal to 0, okay? Those should be equal and opposite to make the forces balance out. Okay, so what you're going to do is that you're going to have a setup like this. Okay? So, now, clamp these down. I didn't have any clamps. So, you're going to have them like this, like so. So imagine that you have something like this. So what you're going to do, I'm going to move these together so they don't tip over. So you've got a protractor. What I would suggest that you measure are these external angles out here. If you want to measure the internal angles and put this like at 90 and you measure this angle and you measure that angle, that's cool too. Or you can go off here. I don't care. Just pick one, okay? Just pick one. So you're going to know these angles, and then you're going to read the scales, and then you're going to have your hypotenuse, okay? So that'll be the first part, and have like a decent angle, okay? Just don't do something wussy like this, okay? Have something like this.
What if it was straight?
So that's going to be your first set of data. Then you're going to increase the angle even more. Then you're going to get a second set of data. So again, you're going to measure the angles, you're going to measure the two hypotenuses. That's all the data that you need for the second lab, okay? So you're like this, boom, and then you're like this. Measure the angles, record the hypotenuse, that's all you have to do.
Can
Okay.
you go any farther?
Huh?
How far can you go before it's like?
Till
Oh, the string's gonna break probably before you do anything.
Oh, wait,
before you-
seriously?
Yeah, that string isn't all that strong. Okay, now, bring the camera, let's go to the back.
Dennis, are you winning?